Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we are continuing to look at Chapter 5 on thermodynamic processes and cycles, but we will be looking at vapor compression refrigeration. The way refrigeration works is basically it is the reverse of a heat engine. Now this means that we are taking work out of something cold and putting it into something hot. And the second law tells us that that's not possible unless we have work input. The CARNOT cycle works it doesn't work, right? It's an imaginary ideal cycle. But if you reverse it, it becomes a refrigerator. And so we can go through all of the steps exactly for this ideal cycle as a refrigerator going one direction, a heat engine going the other direction. But this is simply going to give us the optimal what could be done. So a CARNOT refrigerator is also called a heat pump. That the job of a refrigerator is to take the heat out of a cold something, and the job of a heat pump is to input that heat into something warmer. So if you have a heat pump, for instance, on your house, in the winter that air conditioner kind of reverses and the heat that is being taken from the cold outside is being pushed into your home to warm your house. The basic idea is that you're going to have an efficiency of some sort here, and the best we could possibly do is going to be the CARNOT refrigeration cycle. Similarly to the best we could do with a heat engine was the CARNOT heat engine. When we are doing a cycle, remember that we're starting at a state and making a lot of small processes and ending back at the same state. Therefore, the first law tells us that delta U is equal to 0. And if you look at that for this particular cycle, we had Q at a cold temperature, QC, heat transfer at a high temperature, QH, and then work input. And the sum of the work and the heat transfer has to equal 0. That can be rearranged to say that the net work, or the work input in this case for our refrigerator, is going to be the negative of QC plus QH. So that gives us a balance on the entire cycle. We can therefore use this to evaluate the performance of this engine. Now, in this particular case, we know heat is being taken out of the cold and into the heat, and therefore, if you are operating it as a refrigerator, our goal is to take heat out of the cold stuff, Q sub C. Normally, when we measure performance, so a thermal efficiency for a heat engine, for instance, what we are doing is a ratio of what we get out of something divided by what the cost of operating it is. In this case, what we are getting out of a refrigerator is Q sub C, and what we are having to put in to make it work is the power, or W, the net work in this case. So the ratio of QC over W is going to be the measured effectiveness, and we don't really call it an efficiency. We call it either effectiveness or coefficient of performance. And the reason for that is that this is going to be a number greater than 1. Okay? You do not have to put in as much power as you should get cooling out of it. So typically we're going to expect this to be greater than 1. And therefore that really doesn't match the definition of an efficiency. Okay? So effectiveness or coefficient of performance. Now this is the actual way that you would determine the coefficient of performance for a refrigerator. If you wanted to know what the best possible is, we would do this specifically for a CARNOT refrigerator. And if you look at the second law again, and we recall that doing the second law analysis for our cycle gave us the result that QH over TH equals negative QC over TC. And therefore, we can take our first law balance and our definition of coefficient of performance, and for a CARNOT cycle, we get that this is equal to TC over TH minus TC. Now, this is the maximum possible, okay? And this is going to be for a totally reversible engine, or refrigerator, such as a CARNOT refrigerator, okay? A couple of things that we can observe here. First of all is that if you decrease TC, you're going to decrease the coefficient of performance. And if you increase TH, you're also going to decrease that. So that gives you some limitations there. Another thing is that this is for the refrigerator acting as a refrigerator, but what if you're operating as a heat pump? So, maybe you're huddling behind the refrigerator and your entire purpose is you're going to heat up your room. Okay, this makes no sense. You wouldn't do this. This wouldn't work. But you're going to heat up your room by operating the refrigerator, and that's going to be how you heat the house. Okay, so the goal in that case would be the Q at the high temperature, QH. And so therefore, a coefficient of performance for a heat pump is going to be QH over W. Again, you should get something greater than 1. When we actually try to practically build this CARNOT refrigerator, turns out that really doesn't work so well. But the practical variation on this is called a vapor compression cycle. The intent is the same, but we get down to some steps that just make it not really work all that well. So I've shown here the TS diagram and the 4 processes that combine to make this vapor compression cycle, and we'll talk a little bit more about those in the next slides. I do want to comment here, by the way, that these slides are taken actually from the McGraw-Hill textbook for Thermo, Smith, and Van Ness. They had a very nice, well-detailed set of slides on refrigeration. So let's go over these steps. So the first step was that evaporator. The evaporator is the part that is taking the heat out of your cool substance. It's going to operate at that low temperature, T sub C, okay? And what's happening is heat's coming from this cold material, and it's going to cause a liquid to evaporate. It's going to be essentially a constant temperature and pressure process, and that heat is going to make it have more energy that we're going to then need to dissipate. The next step is that we actually need to do the work input here to increase the pressure. Now, in this diagram, what you're going to see is we have both a state 3' and a 3. 3' is the ideal. So the ideal compressor would be reversible and ideal, which means it's isentropic. If we have an actual one, it's not going to be isentropic. In fact, delta S will increase slightly, and so therefore in the TS diagram, what you're going to see is that the line, instead of being isentropic, is going to be slightly to the right of that. Okay, that's going to be our compressor. Then we're going to need to start getting the material back to our original state. So the first thing I want to do is I have this material that was a vapor, and I've now compressed it, and we're going to then need to cool it back to a lower temperature, back to a liquid. And so this is going to be done in a condenser. This is going to take heat out of the system, and that's going to be what you feel, say, standing at the back of your refrigerator or standing next to an air conditioner that's running outside. And then our last step here is 4 to 1, okay? Now, you may have noticed that these pieces of equipment are very much the reverse of a Rankine cycle. 1 to 2 was our evaporator, and that's the reverse of a condenser, right? 2 to 3 is a compressor. This is a turbine working in reverse, right? It works for gases. For a liquid, I would use a pump to increase the pressure, but these are gases, so I use a compressor. And then 3 to 4 is reversing my boiler, so I'm unboiling this material, which is a condenser. And now then I want to reverse my pump. Now the reverse of a pump is for a liquid, and really the equipment that would be the reverse of that is a turbine. But a liquid turbine simply is a lot of work for very little effort. It's not cost effective, it's a maintenance nightmare. And so instead of trying to recapture some of the work by using a liquid turbine, instead people just use a throttling valve. A throttling valve is essentially a torture device for liquids. Our job here is we're taking a saturated liquid at state 4, and we are dropping the pressure by making it go through a narrowing of a path and then expanding back out so that we get to state 1. This is going to be a liquid, but unfortunately some of the material will have probably vaporized at this point. So it's going to be a saturated liquid vapor mixture at state 1. But now we are ready to again repeat the entire cycle. To analyze this, if we do this on a per unit mass of fluid basis, the specific heat transfer and specific work, Q at the condenser is very easily calculated, assuming no kinetic or potential energy changes to speak of, as just simply the enthalpy at the exit minus the inlet. So H2 minus H1 for QC, H4 minus H3 for QH. The compressor is going to require work input, and again, if there's little to no change in kinetic or potential energy, and if it's well insulated, then H3 minus H2 can calculate the specific work. This gives me enough information to calculate the coefficient of performance, H2 minus H1 over H3 minus H2. Now, let's say you know how much cooling you need. I have a mass of food or a room that's at a particular temperature that I need to cool, so I need to take so many kilojoules of heat from that material. If I have this as a rate, I will get a mass flow rate by simply taking the rate of cooling that I require divided by Q sub C, the specific heat transfer. And this will give me the mass flow rate required for my refrigerant. Now, refrigerants are a little different than our steam. In a Rankine cycle, I was able to work with essentially steam. If I did a Brayton cycle, I'm working with air. Refrigerants, I have a lot of choices of refrigerants, and frankly, that list is growing every year as we try and do a better and better job with our environment. So I want to be sure that I have data. Now this data is going to be, first of all, a little harder to find, but it is largely going to be available in either table form or typically in the form of pH diagrams. Now it's usually actually the log of P, which means the scale is not linear, so be sure you're reading it carefully. And so P versus enthalpy, and they'll do this for a series of different temperatures and a series of different entropies, okay? So temperatures will kind of go across like this, entropies will come down this direction, and we like these graphs for analyzing vapor vapor compression refrigerators, I'm finding that hard to say today, simply because I have 3 to 4 and 1 to 2 are isobaric, so they are straight lines on this graph. And that valve, the expansion valve or the Joule-Thomson valve, whatever you are calling that device from 4 to 1, it is a small device that has no heat transfer, no work because there are no moving parts. Really, you should design it so there's minimal to no change in kinetic and potential energy. And so the first law tells us that H4 equals H1. So you'll notice that we have almost a rectangle going, and then we have that crazy 2 to 3, which is going to be a little less than isentropic, okay? And so therefore we end up with essentially a trapezoid. So that's a nice way that we can look things up on a graph without too much work. Now, there are some comments here on this slide that are about kind of real life. There are, yes, literally some small pressure drops across these devices. They are not exactly isobaric. However, if you actually take measured values from a plant and run those through the data tables, turns out that really you're chasing things in like the 4th sig fig on your calculations. For our purposes, it's not worth the trouble of doing. When we get to doing that level of a design, we're going to be using computerized data sets anyway. The other thing is that this is going to definitely have a lower coefficient of performance than the CARNOT cycle. So once you know what that TC, which is going to relate to the P, the high pressure and the low pressure in your cycle, those temperatures that relate to those pressures are always going to have a result that is less than the CARNOT cycle efficiency or coefficient of performance. To do the calculations, you're going to kind of need a lot of information, but first of all, you're going to need to know the refrigeration temperature, so the temperature from 1 to 2. You're going to need to know the temperature of the surroundings, which is going to give you a value for T4. The compressor efficiency, which takes you from the ideal to the actual state 3. And then the minimum temperature difference for heat transfer. Now, this is when you get to doing a real design. At our course, we're not going to be using that. We use this and cover this in process operations. So we'll save that for a later course. The minimum temperature difference is so that you can have a rational size for your heat exchangers associated with the evaporator and the condenser. The one other thing is that you are going to need to choose the refrigerant, okay? This is section 9.3 in the other textbook. We're going to talk about that in a future video, but as we go through the calculations, sometimes we reach a point where it's like, oh, this isn't going to work. Maybe I've created a solid, or maybe I have pressures that are just crazy. And so the choice of refrigerant is going to be important here. Partly I'm going to want to make choices based on cost, but also on operation safety and so forth. To do the calculations, the compressor is probably the most complex calculation that you have to do because you start by doing it based on the isentropic form of the equation, the analysis. And then we'll use the process efficiency for the compressor to estimate what's going to happen for the actual state 3. So you are going to know T2 and P2, and you can use that to find all of the data here. This is going to be a saturated vapor at the temperature or pressure that was given, okay, or that you've assumed, okay? Then you're going to do the isentropic calculation. You'll know the final pressure for the compressor, and if it's isentropic, the P and the S allows you to find state 3 prime. This can give you the temperature and the enthalpy at state 3 prime, and that will allow you to calculate the ideal work. To find the actual work, use the definition of efficiency for a compressor. So the ideal work, or delta H in this case, divided by the compressor efficiency. Now remember, compressor efficiency is calculated as the reciprocal of what you would have used for the turbine. Efficiencies must always be between 0 and 1. Once you know the real work of the compressor, we can use that to find the actual enthalpy at state 3. That actual enthalpy at state 3 will allow us then to do the calculation of Q in our condenser. This is where they note that this is one of the places where you need to kind of keep an eye on things. Sometimes that P3 that you end up with is, you just look at those numbers and they are alarming. We'll be doing some examples so you can see what I mean by, when you might be alarmed, okay? If the pressure is very high there, the cost of the equipment's going to be prohibitive. The danger to the user, if something were to fail, would be very, serious. And so therefore, you may at this point just abandon the calculations you've been doing and say, yeah, okay, this isn't going to work. I need to work with a different temperature for T3, or I need to work with a different refrigerant. Something is going to have to change in our design. The rest of the cycle is pretty darn easy to calculate. So once you have H3, then all you need to do is the enthalpy at saturated liquid for that pressure is going to give you H4. H3 minus H4 will give you QH. We do know that from 4 to 1 is that throttling valve, and so that is isenthalpic. So once you get H4, that also tells you H1, and we know it's in the saturated liquid vapor region at the pressure of state 2, so therefore we will be able to determine the quality of the mixture at state 1 and be able to find the enthalpy here. Once we find H1, then we can figure out the Q for the evaporator, which is our Q at the cold temperature. Again, this all gets put together to find the coefficient of performance. So Q sub C divided by the work. That's going to be our coefficient of performance. And if we know how much cooling we wanted, then we get the flow rate from QC dot divided by H2 minus H1. So that concludes this video lesson. In the next video lesson, we're going to be looking at an example doing these calculations. Thank you very much for your time.